Good morning to everybody over there. And yeah, today is the second to last day, I believe, of this. So, to not waste any more time, we'll just get started, and I'll hand it off to Benjamin to talk more about machine learning, continuing off from where we were yesterday.
All right, let me get things set up here. Just like yesterday, we're going to be using Google Colab, colabresearch.google.com. I'll make a new notebook here. And here's the link if you guys, actually, that's the wrong link. Here's the link. So what we are going to do today is going to be calculating, or at least calculating, making an algorithm that expects, or that is going to predict the housing price of Boston. So Boston here is a city in the United States. It's in the eastern coast. But it doesn't really have to be Boston. You guys can think of it as basically any houses in your area. So any cities in your area. So I actually do not know which cities are there, but any big cities, housing prices, these things are going to be the ones that dictate the housing prices. And we're going to look at a graph here first. So we're still going to be following the supervised learning method, where we give an input and then we give it a certain output, and it needs to find out what's between them. So how do you get from that input data to the output data, and how do you make that apply for all the data inside your algorithm, or inside your machine learning model. So at the end, it will look something like this. It will obviously vary depending on how we code it here, and that's what we're going to be learning today. So we're going to be actually learning about two different methods of coding. I'll explain these a bit later as we actually get to that place. So this is what our, I guess, data is going to look like. I'll show you the raw data in a second here. But basically, we have a bunch of categories. I actually do not know what the majority of these means. So age here probably means age. Median something. This is probably going to be the price. And I don't know what else that is. PT ratio. Tax probably is actual how much tax it's getting. This is what we're going to be calculating. Median value. I guess that's what line 14 is. So all from every column from column 1 through 13 is going to be columns of input data, and then the output data is going to be line 14, which is going to be what we're going to be looking for. So we're going to get our data prepared, get a model, train the model, and then actually going to do how to use the model. It will be a slightly different way from yesterday on how we actually use the model. So follow carefully. All right, so let's first lay out the steps that we're going to be taking today. Let me pull out reference here. All right, so we're going to first start with importing modules. And the next, we're going to do data preparation, so importing from our CSV file. That's going to be our second step. Third step is going to be creating independent and independent variables. Or independent, I guess independent goes first. Independent and dependent. Okay, I misspelled that. The independent and dependent data. And then next we're gonna do. I should. Next we're gonna do creating the model, which is gonna have a lot of interesting stuff today. We're gonna mess around with how different models are created and how we can actually make it a bit more complicated or a bit more simpler or make the process longer, make it run faster, those kind of things. We're gonna try those. And then we're gonna, like yesterday, do model training using the fit command. And then we're gonna actually use the model. Oops, I did not intend to run that. And then that should be about it. There's gonna be multiple layers to this, so let's get things rolling. So importing modules, just like last time, we're gonna need our basic modules. So that's gonna be import TensorFlow, which is our machine learning model, TensorFlow. This is gonna, as we learned yesterday, actually let us do the code as TF to make it simpler so that we don't have to write TensorFlow every time we try to do things. Import pandas. We already learned pandas as PD, also to make it shorter and simpler. Import math. And that should be it. We hit run. And then that should be the basics of importing the module. You can obviously name the TF and PD to whatever you want to. So you can theoretically name it T and just P without TF or PD. We just recommend doing these because this is like what we use universally pretty much. TensorFlow is usually imported as TF and pandas is usually imported as PD. It's not only universal, but it's also easy to understand. If you put T, there might be some module that also starts with a T that makes it quite a bit more confusing. Instead, we can use TF, which stands for TensorFlow pretty clearly and shows it pretty well. So that would be importing module. Second, data preparation. So I will send the data in the Q&A chat right now. Oh, this is a screenshot. This is going to be the data. So if you actually look at the data, it's going to be a very complex series of numbers. So up top, we have which order they're layered in. So everything on the first 13 from crim to LSTAT. So the first 13 float is going to be the independent variables, and the median V or median value, med V, is going to be what we're calculating for. So that would be the dependent variable. So data preparation, this step is just using basic pandas. So it'll be data. So first we're going to do data path. So this is where we're getting the data from. Quotation marks and copy paste the link directly in. So it's a complicated link, so I'd highly recommend just copying the ones in the Q&A chat and then just do quotation marks and then paste it in the middle. Then next we're gonna name our main, I guess, our variable that stores all the data. It's gonna be Boston. So we're gonna name it Boston because it's Boston housing prices. Because that's the name of the question and that's what we're calculating for. If we're to do a different city, that would be obviously different. New York would be, we could just do it as New York. We could just do it as London. That should be good. So Boston, we're going to do PD for pandas.read underscore CSV, because this is a .csv file, as you can see here. And then we're going to do data path, because we're reading that particular one. So realistically, you really don't need this data path variable. You can just paste the link here. But I guess to make it more interchangeable, to just make it a bit more easier to visualize, we're doing it this way. And then we're gonna do print Boston.column to check out what the columns are. These columns are going to be important because not only is knowing the number of columns important, but we're actually going to manipulate them a bit later. And then we're going to do the first 5 lines of Boston.head. That will show you just the first 5 lines to see if we got the data imported correctly. So let's run it. Yep, as we can see here, Boston.columns, we got crim, zn, index, blah, 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 all the way to med v, median value. And then that is going to be our columns, or that is also going to be the names of our independent and dependent variables, dependent values. And then here we got the first 5 lines showing us what they are. All right. So next, we're going to set our independent and dependent data. Pretty simple. This is just like last time. So we're going to first make a create a variable called independent. Independent equals, and then Boston. And then it is a double brackets here, double big brackets here, because we're trying to make this in the 2D list, because that's what this program accepts. And then we're going to fill in the names of Boston, the first 13 of Boston columns. So it'd be prim, vn. Basically, we're copying whatever is up here, so we can actually just do copy to lstat. Because remember, medv is the dependent, that's the value we're trying to get. Everything before that, we can just hit Control-C. And then Control-V into here. Make sure the format is correct. And then next, we're going to create our... make sure there's no tabs here. So because it didn't extend all the way, there's a tab. This will not work with Python. So make sure to get rid of the tab. And then we're going to set our dependent to be Boston. And then medv. This is buggy today. So that is going to be dependent. Remember, median value is the value we're trying to get out of it, or we're trying to predict. And then to check if they're in correctly, we'll do print independent.shape and dependent.shape. So if we run this code here, it gave us this 506.13 and 506, 1. So what does this mean? It means there's 506 lines of data. So I can actually show you guys this in a replit file where, you know how most IDs can actually show lines? We can use that feature in replit. And I'll move the replit window over here. So if you look at this replit window, and then we in this tab, hit the blank space and do Control-A. It will copy every single data in here, even the things that you can't see, so all the way down there. Hit Control-C, and then copy it over Control-V. So if you look all the way down, there's 507 lines of data. It only says 507 because this one actually includes the top layer. So if we go all the way up, see as it includes the top layer. So if we get rid of this top layer, it would actually be 506 data points. That is what it means by 506, 13. So it's 506 down of 13 independent data. And then it's going to be one dependent data, just one of them, and then 506 dependent data below it. That was pretty simple. And the next part in theory is also relatively simple, but we'll run into another roadblock here. So we're going to do basic XY using perceptrons and formulas. I'll explain what both of these are in a second. So from what we did yesterday, the default formations look like X equals TF, remember TensorFlow, dot keras, dot layers, dot input, and then shape equals 13. Can anyone tell, does anyone remember why it's going to be shape 13? It's a, number 13 has been used quite a bit in our coding. Just in the Q&A chat, what does the 13 imply? What does shape 13 mean? Why is it 13? To give you guys a hint, it was 1 yesterday instead of 13. What changed? What made it 13? The number of datas, the name of the data, number of rows, number of columns. Any ideas? Alicia said. Number of columns. Almost perfect. Shadrach typing. Let's hear from Shadrach before we move on, and I'll tell you guys the answer. So the Shadrach, we'll wait for you for a second here. Let's see. Number of columns. All right, we got the two same answers. It is the number of columns, but the number of columns from the independent variables, or independent data. So there's total of 4. Wait. 1, 2, 3, 4, 5. Yeah, there's total of 14 data types here. 14 lines. So 13 is for the independent. So what we're trying to calculate, that's why it's shape equals big brackets 13. And then just simply y equals tf dot keras dot model, no, dot layers dot dense 1 and x. So what dense is doing is it's adding a layer of processing. So dense 1 means, so keras dot layers, so it's basically adding another layer. Dense means it's actually calculating using that layer. So the input, so x we just set as tf dot keras dot layers dot input. So dot layers mean it's the first layer of data, and that's going to be the input data. But we did that by using dot input. And then y is going to take in x, and it's what it means by dense is it's calculating it. So it's adding a calculation layer, and then the dense 1 here means it's getting 1 output. It's giving 1 output. We'll also mess around with a bit of the numbers here. I'll explain in a second here. And then next we're going to do model equals tf dot keras dot models dot model x and y. And then next we're going to do actually run the model where we're going to create the compiler for the model. So it's going to be model dot compile loss equals MSC. So loss equals MSC. what this means is it's losing or MSC means it's mean square error. So mean square error, to explain briefly, this is not really important. There's a ton of different of these type of loss equals. There can be a lot of things that go in here. MSC just means it's getting its difference between the prediction and the actual correct data that we're feeding it, and then squaring the difference between the real data and the predicted data, and then doing the average of that. That's what loss equals MSC means. And then we're just gonna do then we're actually just first let's run this one, create a model. Should give you about 0 seconds here. Next, we're actually gonna run the model doing model.fit. And then we're gonna do our independent, dependent, because we named it just independent and dependent. Dependent. Then we're gonna do epochs is 10,000, 1,000 here. And then verbose equals 0, because we do not want to see 1,000 different epochs being run. And then we'll do model.fit, the same one, independent, dependent. And then we'll do epochs of just 10 to just show us what the result looks like. What does our loss look like if we run it like this? It'll be a bit interesting. Last time, remember, as closer to 0 the loss is, the more accurate the data is. Because it's the different, so because loss is mean square, because loss is mean square error, MSE, mean square error, MSE. So it means the difference, so obviously smaller is better. Square that, so still smaller is better, and then the average of that error. So it's smaller the better. It is taking a while, so it took me 41 seconds to finish this one. And as you can see, our loss is quite high, 27. So that means the average of the difference between the real data and the expected data, so the difference between the two, that squared, so that would be the difference times the difference, so squared. And then the average of that is 27. That is quite high. That means usually the data is about 5 off. And remember, guys, this is median value at 24. So considering the housing prices here, this would be around, I'm gonna say $2.4 million. So 24 would be 2.4 million. Actually, let's just go with a simpler number. So 24 would be 24 million. 21.6 would be $21.6 million for a house. 34.7 would be $34.7. $34.7 million is going to be the median average for that particular neighborhood inside of Boston. So a difference of so because this is an average of the square, if we square root it, we'll get a number that's slightly bigger than 5. That means the data is off by $5 million. That is massive. That's a huge chunk of money that's being different. That means it's not accurate at all. So why is this? Go and take a look at what our slide has said. Okay, it doesn't actually tell us that much. So what it could be is that some of the data just does not make sense. It does not impact it enough, and it's wasted data, and our program is catching on to that wasted data, and it's trying to calculate it with the wasted data to give us a loss. So what do I mean by wasted data? What exactly is wasted data? So it just means that something just does not matter. For example, usually the fact that the house has a pet usually does not change the value of the whole neighborhood. It might, but it also might not. But if it's included in data and the algorithm thinks, oh, I have to calculate using this data too, and then calculates while using that data, becomes a pretty big problem. Because it's incorrect data. It's not useful data. It's just there. So a good way to fix this would be just brute forcing it. And I'm pretty sure there's also algorithms that do this as well, trying to fix these kind of wrong data here. But we're going to go over a couple more things that are important for our lessons here. So first of all, we're going to temper around with the number here. Dense 1. Like I said, dense 1 means it's going to give you, it's giving you 1 output. So that whole thing of 13 data is all within an equation down to 1. That is what it's doing. But if we change this into 2, watch what happens. So we got to run this part of the code again. This is done in order to make it faster. And then I will probably reduce the number of epochs for the next one because we can't sit here waiting forever. But let's run it this time again, and then I'll reduce the number of epochs. It theoretically shouldn't change the performance, change it that much, but let's wait. Remember, the number right after dense in the parentheses, the number of outputs it's giving. Let's see if we make dense 2, what it does. Oh, that's not what I was expecting. Okay, so this is basically gonna do us the same thing. So what this is doing is, we look at the side here, it looks something like this. So making a dense of 2, it's gonna add another Y2 layer that is not used here. Oh, okay. So in order to get this one working, we actually leave out one of the Y layers. So the way we're gonna do this is, if we go back here and change the shape to 12, so we're gonna see maybe one of them is an output number. So let's say, so we have our little table here, but else that isn't really related to median value, but rather we're going to get both LSTAT and median value from, we're going to extract both LSTAT and median value from this program. And all the rest of them is actually what we're trying to get. It's going to be what the algorithm is going to be calculating. Then we'll just move LSTAT down there, because LSTAT is going to be now chosen as a dependent variable. Yes. And then we're going to change the shape to 12 because now there's 12. And then if we run it like this, okay. Did not like that. Oh, because there's one independent. Okay. Let's do it without this. How's that? And this again, and this again. Did I? hmm. Uh, Give me a second here. Run this part again, this part again. All right, there we go. Now it's working. So remember, guys, so shape is the number of independent. So we have 12 now because we put dense to 2, meaning we're going to get 2 layers. So we're going to get 2 outputs. And then because y is now 2, the model xy is going to be 12 independent and 2 dependent. So it prints out the same thing, but in the actual model, it's going to have more or less of uh, the both of the variables. So let's actually print out the model first. So we're going to do print model dot predict, because the model is already created here, independent. Let's just do our first data, 5 to 10. So that we can actually go back at it and easily reference this. And if you run this one, it gives us 2 output pairs. 9.34, 23.2, 10.6, 21.2, 13.9, 20.1, and more. And with more decimal places, obviously. So let's see if these align with the actual data. Get here. I will make this a bit easier to see. So line 0, and it'll be these. I'll copy these over to the side, and then I'll show you guys in a second here. Remember how our error was quite high? This is going to show if the error is actually high or not. We go back here. So if you actually look at the data, I'll move up the data here in just a little second here. I cannot copy data apparently. Okay. So the data, the resulting data is 2.94, 33.4, 5.33, 36.2. You can already clearly see that it's not accurate at all. 28.7. And it just goes on from here. You can see that the data is just completely off and different. But that's all right. That we are just trying to get the hang of our algorithm here, and then that was actually a part of this problem. So this is how you get 2 outputs. So the first one will be the LSTAT value, because we said LSTAT here and then medv here. This will be LSTAT, this is medv. We can use this to output data in a more predictable way. So what we could do is we could set this to a variable, and we would do value equals auto.predict. So in order to manipulate it, slightly complicated. Let's just do value.type to see what it is. What exactly are we dealing with? This is numpy.ndArray. I do not know what this exactly stands for, but we can still manipulate it as a list in our case. So let's get rid of this. Now let's do for I in value. Okay, I actually pressed the wrong button. Print I. What would this do? Instead of giving us a one big list, so print value. Instead of a list contained by two big brackets on the start and end, it gave us a list. It's not strictly a list, num_feed_array, that weird thing. But at least it's improved. Now we can manipulate it further. Because we know this is this, then we can do for j in I. So because, remember, a bracket with no commas, we don't deal with this usually. It's only enters or space. But this command seems to work. Let's use it. So for I in value, we got each one. And then for j in I, so for each value here, we can do print. Let's do else that is, and let's do this. And then medv is this again, dot format. Let's do okay, so what we're gonna do is let's do what else that is first. So if we do this and dot format, let's go step by step here. Run this one. So we can see that we have successfully manipulated this into a form that we can understand a bit better. Obviously, this second one is medv, not else_that, so we have to manipulate a bit further. Let's try range commands and let's try indexing instead of getting them all at once. Or if it's indexing, actually we don't even have to use this one. So we can just do print this and then do instead of just else_that, we can do medv is and then dot format. Since there's two variables, it would be I0 and then I1. We got the correct value. else_that is 9 this long number, which it's shown here correctly. medv is 23.20465 as shown here, correctly shown. So we're actually correctly manipulating this weird numpy list type by using format to manipulate the string, and also just using .i in value, and then just using simple indexing. Simple as that. Python is quite interchangeable, especially depending on how you code it, and this shows, well, it was very interchangeable, and it worked out pretty well. So this is the first part. Let's see a visual diagram of what we're doing again. So we're doing this. We got 12 inputs from crim to b. And we got two outputs of y1 and y2 of else_that and medv. That's what we just did. Should be simple enough till here. So we're getting two output pairs because we set the dense to 2. And because there's now two output pairs, and because we took one of the outputs from the independent, we have to reduce the independent from 13 to 12 because we got rid of one. And then that should be it. Next, I'm going to teach you guys one more thing about how to use dense and manipulate your code further. So we only so far have, let's return the code here. We so far only have one layer of processing, one dense layer. What you guys need to know is that you guys can actually have multiple dense layers. Multiple. So how does that work? So if you look at the dense layer here, let's dissect this one by one. TF is TensorFlow. .keras is just a module inside Keras. No, it's just a model inside TensorFlow that lets us do AI stuff. It lets us do machine learning stuff. And then there's layers. How many layers? What layers is? It means we're just adding another layer to the machine learning algorithm. So there's an input starting layer, and then the output layer. And then we got dense, which is just creation of a layer. And then one, meaning we want one output from that layer. So if you look visually here, this whole thing is a layer. This is a layer. Thing inside here will be dense. So we're doing that. And then one means give us one output. And the next X here is the input. What is the layer before this? What are we getting to? If we use this, think about it. If that's the input, what if we just set this to another X and then run it again? Let's do X equals tf.keras.layers.dense and then do the same thing. Does the exact same thing. Or rather, as a whole new layer. And then we would have to finish it up with y equals tf.keras.layers.dense 1x. So we just added multiple layers. And they all lead up to y. So we got layer x. Let me show you a different diagram for this one. Give me a second here. Just make a quick copy. And then I will show you guys a diagram. So we can see we got an input layer, which is what we used as input in the first line. So there's keras.layers.input. And then we got the first dense layer. So this is the first dense layer, but its output is 1. The next one's output is 1. Do you guys see a problem here? So what we're trying to do here is we're trying to make it go through different routes. 3 different routes to get the most accurate algorithm. 3 different routes. And then eventually to a final layer of outputs. But if we have 1, just shrinks to 1, and because the next one is also 1, just goes to 1. Nothing changes. That is a problem. If it's 1, 1, 1, 1, it's the same thing. You're just following a straight line. Instead, what we do is to make this to a bigger number, like 10, and then 10. And let's do 5 for the last one. So visualizing what this looks like. So we'll start with an input layer. We have 12 data. We have 13 data here. Go into 10 of these dense layers. So instead of only 3 circles, as you see on the screen, there would be 10 circles for them to go into. We go in there. And then the next layer, because we have another 10. This should be 1 actually. Because we have another 10. So we got 13 inputs, two 10 layers, to another 10 layers that goes interchanged. So just like this one, it goes all over the place. And then finally to an output of 1. That is what we're doing here, adding multiple computational dense layers. And then, but because this model is quite inaccurate, I don't think this will do much. If we run the model here, interesting. Was not meant to happen. Oh, okay. We forgot one part of the command. So actually using dense layer, we have to do something called activation commands. We're going to be adding something called activation swish. I misspelled that. Activation swish. Oh, swish is should be in double quotes. Activation swish, and we're going to add this to the end of both of our dense layers. So what does activation swish do? So the swish function just is a way for this code to understand each other. So it's I don't know how I would explain this perfectly. So, but swish function is basically it lets you manipulate the data a bit better. So it's a output that the code understands. So just like how we use shape here, and we're using a double list here of pandas, swish makes it that the output is something that the code itself can also understand. Still not running. I did okay. I don't know what exactly is causing our error here. I lost see. Go swish. I currently do not exactly know what is causing our problem here. Oh, okay. So we have to actually take in this with a different input of not x, but rather a different variable of h. Not how I expect this to go. And then, although we added multiple more layers of multiple more hidden layers, so X would stand for input, H would stand for hidden layers that we see here. It's called dense layer here. I'll show up a different diagram. It's called hidden layers here. So that will be what H does. Hidden layers, and then Y. So your model. But as you'll see here, it will not really make that much of a difference. It'll take a while. Yes, it does not. The loss is still incredibly high, and we did not get much of an accuracy benefit. So in this case, it didn't really work. But this could work in different programs. Okay. Oh, this be X. All right, so while this is running, I'll explain this a bit more again. Sorry for the confusion. So we're going to do x equals tf.keras.layers, and then we're going to take in x, which is our input layer, get that into a hidden layer with the activation swish, and then get that hidden layer, run it through another hidden layer, tf.keras.layers.dense. So if we go back to our diagram here, x is here, hidden layer 1 is here, hidden layer 2 would also be here, and output layer would be here. And then this hidden layer would have 10 nodes. First input has 13 nodes, shape 13, then it's 10, 10, then 1. And we can see that our accuracy actually has increased pretty significantly. Instead of being 26, now only 14. That is a lot more accurate. By using hidden layers like this one, and if we actually add another hidden layer, this will probably take a way longer now. Do it again. This will make it, as you run it, do it more and more and more times, it will make it more accurate. So, but will also take a bit more time, and such and such. So that's what adding hidden layers, usually named it by H, does. But H, you run it through multiple times, and then so we set it to hidden layer H, and then we get H, we put it back into another H, and then using that H, we put it into another H or hidden layer. And then finally, when the last hidden layer is done here, we put that into our final output dense layer. So this output layer, that's where what Y is. And as you can see, although we reduced our loss by around 2 now, from 16 to 14. But you can see before we went down from 26 to 16, and we can see that it hasn't changed as much. So that goes back to our original problem of this data having a false data that is not entirely true. So that is what this is doing. Model.training. And then that was the explanation to hidden layers. So a quick recap of what we just did. So first of all, by changing the number dense here, so instead of shape 13 here, we did to shape 12. So instead of 13 data as input, we took 12 data as an input, and then the last two became dependent. So the last two things are the things that we're now, the last two layers are now new dense layers. So that's what we're doing. So that was manipulating the number of dense layers here. And this also came in handy on the next problem. Because we actually have, as you can see here, 10 now. So that's what it's doing. It's we have a input layer of X here. And then we have 3 hidden layers, and then the output layer Y. Input layer X, this has 13, and then this has 10, 10, 10. So it'd be hidden layer of 10, and then another 10 hidden layers, and then another hidden layer that has 10 different nodes. 10 vertically, as that'll be so P1 to P10. And then finally, the output layer is only 1, because we are only getting one output here of medv. That's what this program is doing. And as you can see, the program became quite a lot more accurate. Instead of loss of 26, it's now only 14. Remember, the closer to 0 it is, the better it is. But we weren't able to get it to 100% accuracy, which goes back to the issue of this data of Boston housing price as something that's not really useless or something that our program cannot really do. So like things like age might not be a big issue, or knocks, whatever this is, could be a wrong data that's not really that shouldn't be part of the equation, but it is. It's just useless data, but it's there. So it's making our program matter. So that would be the normal problem, and that should be the issue. Uh, Give me a second here. So that would be our Boston housing price example. Uh, Guys, give me a quick second here. All right, we'll continue on to our next data here. I just went slightly too far, but all right. So this was our Boston housing price, and this was our hidden layers, as well as getting multiple outputs here. And then, so the next one would be, let's create another one, a new notebook. So you guys can just come up to the, so you guys can just come up to the top, hit File, and then there's a new notebook button. Click that one. And next, we're gonna be doing. Let's name this to Iris Flower because that's what we're gonna be doing. Iris Flower. And let's start generating our code. So just like last time, we're gonna start off with the exact same things of importing modules. So import modules. So we'll lay out the old order first. Importing modules, and then data preparation. So that'll be importing from our CSV file again, and then just putting them in the correct order and the correct places. And then setting independent data and dependent data. Independent data, independent and dependent data. And then the next would be next we're going to manipulate with how this data is a bit different from what we're used to doing and how we're going to use that one. And then, so this will be a secret. We'll learn about how this works a bit later. And then we're going to do create a model. Create model. And lastly, we're going to do model training. So we're going to, this is the part that you guys just didn't wait, model training. And then we're going to use the model for actual prediction. All right, let's start importing modules. Just like last time, it is identical. So import TensorFlow as TF, import pandas as PD, import math, data preparation. So I'll send you guys the link to the data right now. In the Q&A chat. This is the data we're going to be using. If you click this, it should give you the data. So let's have a look at this data for a bit here. So if you guys click the link, you can see we have petal length. Oh, for reference, guys, this is an iris flower. So let me actually show you guys what it looks like here. Give me a second here. Here we go. I'll move this to the correct window now. All right. So this is what an iris flower looks like. And there's three types. One that looks like this, iris versicolor, iris setosa, and iris virginica. So as you guys can see visually, they look a bit different from each other. They're a bit different. So how do scientists know, and how do machine learning can help us here? So we have our data here. This is not exactly the cleanest data I've seen, but to reduce it, we have petal length, petal width, pole length, sepal length, width, and variety. So we got our petal here. So this is the petal, the one that looks more like a leaf. And the one with more colors and yellow on the down here is going to be our sepal. That is what we're doing. So we have petal length, so that would be this thing's length. And then petal width would be the length of this thing. Sepal length, sepal width would be this, sepal length would be this. So we got 4 different type of columns. And then we finally got the variety. So this combination of flower type is setosa. This combination is setosa. This is all setosa, meaning the middle one. But if we actually see our raw data here, we can see setosa, versicolor, virginica, setosa, versicolor, setosa. List continues onwards. So this is going to be a classification example. So in lemonade sales, just telling us if what temperature it's going to be. Classification, we're actually classifying these into each flower type. So what we're going to be doing, as we can see from raw data here, we're going to get the data of the petal length and width, sepal length and width. So petal length and width, and then sepal length and width. And then we're going to get which variety it is, the name of it. And then we can, so it's going to be classification. So we're going to be classifying this is that, this other one is this one. So the model is the same as before. So let's get coding. Iris flower. Data preparation. So going back to our original one here, we're going to do first data path. So this is our data link path. Like I told you guys before, this is not strictly necessary, but it's better to do it this way. Iris. Our model name is now Iris, or at least, or our data name is Iris, because that's what we're going to be using. Is p equals pd dot read csv. Remember, this is a .csv file. It means comma separated list. If you see here, let me clear out some tabs here. It is a list separated by commas, and then there's the name of the list here. CSV, comma separated lists. Comma separated, yeah, variables. .csv, and then we're going to read from the data path, which is just this link here. It's just a string leading to this link. And then we're going to do print iris.columns to see what columns we have. And then iris.head, we only want to see 5. We don't want to see the whole thing. So run the first one. Okay, I gotta kill some sessions here. All right, let's run this one. Oh, we gotta run the first one first. Let's see. So run the first one first, importing modules. TensorFlow is a pretty big module, so it usually takes a while. It's also the modules are. So this is all running on Google's computers. So if you see here, it's 12 gigs of RAM. So we're using Python 3 Google Compute Engine backend. So it has 12 gigs of RAM and 107 gigabytes of disk storage. That's what it's doing in the background. But even with that, it takes a while. Data preparation. So we can see here, we've got payload length, payload width, sepal length, sepal width, variety. Everything seems fine so far until it's the next part. Just set it to independent equals iris. So the first data first columns except the last one. So variety would be deleted. Remember to make sure that you're not indenting stuff incorrectly, because if you just copy paste it, it's an incorrectly indented content. Then go to dependent equals iris and variety. Oops, I missed. This is not how you're supposed to do it. So if you guys look at this thing, something is a bit different. So just like before, we'll just do independent dot shape to see how, just to see if we are doing this correctly, and dependent dot shape. Run this one. There's a total of 150 lines of data. I showed you guys last time how we can do it via Replit by doing Control A, Control C, and then putting it into Replit and then seeing the and then seeing the line count. We'll just trust that it's 150. It's a lot shorter than last time, so we'll say it's 150. But now we have ran into a problem. We have 3 different words of variety. We're not looking for a number here. We're not manipulating with numbers. Everything before we used, it's all numbers in the middle. And now the output is also a number, because this thing computer only does numbers. It does zeros and ones. And those zeros and ones become numbers, but in order to calculate stuff, we use numbers. Think of it this way. We can all, if you're doing math calculations, yes, we do use x as a variable. But do we use Word? Do you use things like, I don't know, Boston in a calculation? Is BOSTON mean anything in a calculation of a math calculation? No, it doesn't. You cannot just do x times Boston. That does not mean anything. You can do x times 5, and that would be 5x. But x times Boston, and we're taking Boston as not a variable here, as like the word Boston. So to not confuse you guys. Also, this is the wrong one. Let me get rid of this one. So to not confuse you guys, let's say I have an Android. So Android times 5. In a coding sense, if Android was a string, it would just do 5 Androids. But just think of it mathematically. Think of it as a mathematical equation. What does Android times 5 mean? It's a word. It doesn't mean anything. Same with computers in a mathematical calculation. This thing, Satosa, versicolor, virginica, Satosa, means nothing. We gotta convert them into actual numbers that the computer can understand, or actually output them as numbers. The computer gets it. So then we're gonna use our secret here. So what this is doing is, if we look at, we're gonna use something called .getDummies. I'll show you guys what it does first. pd.getDummies, iris, c key, iris, print iris.columns, then iris.head. So iris is now pd.getDummies iris. So iris has been converted into something using the getDummies command. What did it get to? Now we can see. Let's see the difference here. So let's fit this into one screen. So before we had petal length, we had variety, and just the name of them. Was Satosa, versicolor, virginica, Satosa, and versicolor. But now it's named variety underscore Satosa, variety underscore versicolor, variety underscore virginica. So you can see, it actually converted us to a number format that we can actually use. So Satosa, the first one, the line 0 is a Satosa. Satosa is 1, the rest of them is 0, 0. So remember, in a computer sense, 1 is yes, 0 is no. We did this before in Python, actually. We learned about how if an integer is true or false. Remember, anything that's not 0 is false. Is true. So 0, 0, false. First, it's only Satosa. Versicolor. The second one is a versicolor. The third one is virginica. So it has a 1 here, 0, 0 here. The fourth one is the third line, line 3. Remember, it starts from 0. Line 3 is Satosa. Satosa is 1, meaning true, and then false, false. And then line 5 versicolor is, first you can see the variety versicolor is highlighted to 1. That's 0, 0 before and after that, because it's versicolor only. So .getDummies command gives you new values from the value already given. So you wait to identify it as a number format in order to make it possible to code it. Because remember, you cannot do words in a mathematical equation. You can have variables, but you cannot do words. You cannot multiply your computer by 5. That's not how math works. So Aries is officially turned to this one. So then we can manipulate with our independent and dependent variables a bit more. So let's add another code line and do redo, redone, independent and dependent data. We're going to set independent to the same one as above because nothing really has changed about independent data. But now now dependent data has to change a bit here. Oops. Iris. We already printed out iris.columns here. We're going to use the new column data, the last 3 values of identifiers. And we're going to do iris.head. Then if we already did iris.head above, but if we just do it again to see if the code is working, doesn't really. Okay, now this one does not run. So remember how I told you guys this is code snippets? Here, Iris was already set to a different one. This one no longer works. Variety does not exist. This code is garbage now, so we can get rid of it. I need this one more time. It's code snippets. You can run it. The order you run it in is the order that the code is going to be running. It's how the computer stores it. That's why it needs an actual disk of storage. So this is now useless because Iris is no longer variety, but rather, well, Iris variety does not exist. It's rather variety underscore setosa, variety underscore versicolor, variety underscore virginica. This is useless now. Let's get rid of it. And then we got the correct data here. Now let's actually create our model. That shall be. So we're going to create the simple model first here. No hidden layers, no goofing this time. Keras.layers.input shape equals 4. There's 4 inputs here. We have 4 petal length, petal width, cycle length, and sepal width. Then we're going to get y equals tf.keras.layers.dense. Tell me what number goes in here again. What does this mean? You guys can either tell me what number goes on here, like what it is, or you can tell me what the number going in here in this particular program should be. Is it a 1? Is it a 2? Is it a 3? What are we getting? What do you think we're getting for? I'll wait around a minute or so to let you guys think, but I'm not 100% expecting you guys to remember everything I say here, so I'll wait around a minute here. I don't think anyone really remembered. So remember, dense is the number of output layers. Oh, okay, Shadrach's typing. I'll wait a little bit here. 1, 2. Okay, we got different answers. 3. Or are we just counting up here? All right, so let's see how these work out. So this is the previous slide, but we can still use it. So that is 2. Gave us 2 outputs. And we had 2 dependent columns. 2 dependent columns. How many do we have now? We have 3 dependent columns. These are all result columns. So we need 3. We need 3 of them, and then we're going to take in things from X. Remember, so we have 4 here. So we have 4 here. And we have 3 here. So this is 3. We need 3 output pairs. So it's going to compare when it's 1, when this is 0, when this is 0, how it all lines up. And when this is 0, 1, 0, how it lines up. We're going to see all of that. The machine learning is going to do all of that. And then let's finish the coding. And I'll show you, you also have to add another one to here. We'll show you that in a second as well, what that does. So we're just going to do creating a model. Model equals tf.keras.models.model xy. This might error out or it might work, but it will give us not the result we're looking for. Model.compile. Loss equals categorical cross entropy. I'll also explain what this complicated word is. Metrics is going to be accuracy. I'll explain what all of these means a bit later. There's also something, I'll also explain something. Okay, then we're going to do model.fit, independent as our x data, dependent as our y data for the output. Epochs, we're going to set it to 1000 for this one because we don't have a lot of data in the first place. Verbose is 0. We don't want to see 1000 epochs being printed. Model.fit, independent, dependent. Epochs is going to be now 10 and then we're not going to put a verbose here because we want to see what the accuracy is or what it's actually printing. This might give us an error. I'm not sure because we're missing something here. All right. Got loss of around 5 and accuracy of around 0. Nothing seems wrong so far. Actually, let's print out the model. Let's just use the first 5 because we know what the first 5 is. Let's just use that as reference. Print model.predict independent. And then we're going to index it from 2, 5. We run this particular set of code here. We already have a model. What is the error? I expected this to be an error. Oh, we made a typo. That's not the word I wanted the error to be. Yeah, so give us a bunch of numbers. Something's wrong here. We're not getting number. What are we? Let's go back to what we're looking for here. We're looking for 1, 0, 0, 0, 1, 0, 0, 0, 1. We're looking for zeros and ones. We're not looking for whatever that number is. We're looking for it. Oh yeah, so we're looking for it. Something's not right. We should be getting 0, 1, 0, 1, 0, 0, because it's predicting. 5 is not a prediction for a 1. What does -3 mean? What does 2 mean? We go back to this one. Well, you can actually you can actually get the data out of this, but it's not what we're looking for. We're going to do something called comma. So when we're doing hidden commands, we're using swish. Instead of swish, we're going to do activation equals something called softmax. Oh, by the way, number 3, output is the correct. So Alicia, the fixed answer is correct. And then Shadrach, first time around, you got it correct. It's actually 3 because we have 3 dependent data of variety underscore Satosa, variety underscore versicolor, variety underscore virginica. Because we need 3 outputs. There we go. Activation softmax. So what softmax does, among the list of possibilities, it gives us the maximum. It gives us the most accurate value, assigns it to 1, and the rest of them to 0, 0. 1, 0, 0. Exactly what we're looking for. That is what activation softmax does. There's a bunch of activation, like a lot of them. So before we used activation swish when we're using hidden commands, just another one of them. Softmax, there's a bunch of these. The use of them will also vary depending on situations. So we create model, softmax, and then we will redo the model training. I'll wait a bit here. Categorical cross entropy. Metrics accuracy is just how accurate it is. Loss categorical cross entropy just means that it's calculating the loss between the labels and predictions. It's just calculating what the actual value is and what the prediction value is. It's just another way of measuring the difference. If you use the model now, it is still a bunch of useless values. Okay, that's not exactly what I was expecting. Okay, so it is still a bunch of useless values, but we can actually extract a lot of things from here. This may look complicated at first. Let's do only one of them. All right, we got one value here. If we just look at this line carefully, we got a bunch of decimals and an e minus 0.1, e minus 0.3, and e minus 0.7. So this is actually a pretty relatively advanced math equation words. Basically, what it means is how much zero it's shifted up or down upon. So if it was E5, let's say if it was E1, this would be 99.8. It was E0, that is what we normally use. So think of it, 5E0 is 5. I'll show you guys here. So 5E0 is 5, and then 5E1 equals 50. 5E minus 0.1 is 0.5. 5E2 equals 500. And then 5E negative 0.2 equals 0.05. So it just basically means how much trailing zeros do at the end of it, or how much decimal point you pull it down by. So even though, well, this is pretty clear by itself, this is obviously the biggest value. But it also has -1. These have -3, -7. So this would be a 0.99876 and a 0.0. So it would go down by 1. This would be 2, 3, 1, 2, 3, 3, 5, 3, 5, and that would have 7. 1, 2, 3, 4, 5, 6, 7, and then 1, 2, 7, 6, 9. You can see this is clearly the biggest and clearly the closest to 1. Oh, let's comment these out. How do we use this? So sure, we can look at it. Well, the first one is obviously the biggest. But we actually want to see the values for ourselves. Then we start manipulating the code, the finishing result. So we would do value. Let's do value for I in value. Okay, in order to do this properly, let's make this around like 3. If we run it now, it'll give us 3. Oh, okay. I did not print anything out. Print value. Give us 3. So we can see if we do type value here, this is going to give us the weird one that we numpy.nd array. We can basically use this as a list. So we're going to do for I in value. Oopsie. Value. If we do print I, interesting. So if we do this one, we're gonna get print I, and then we now have individual, and then if we do print type I, we have individual numpy.nd arrays. Let's get rid of this. And then let's do. So now we know that we can get this down to individual values. So if we do for j and I, print j, now this is going to give out individual values. So these 3 will be the first, these 3 will be the second value, and then these 3 will be the third value. We know this much. Now, we have to actually know which one is the highest and which one it equals to. We can just use a simple if statement. Remember how I said these are basically as lists? You can index them as lists. So I is one of these lists. So this is our first I. So if I0 is bigger than I1 and it is bigger than I2, this is not how you write end in Python. And then we can say, because that means the first one is the biggest value. What is the first one? It's variety Setosa. So it's Setosa that's the biggest. So then it would be, we can safely say that it is print Setosa. Because we know because it has the highest probability of being a Setosa, because it has the. So remember how we said metric is accuracy? Well, highest probability. Highest probability. And then else if, oops. Else, so we now know that 0 is definitely not the biggest. And in machine learning algorithms, you rarely ever get values that are identical. Or it's impossible to get the values that are identical considering how deep it goes. So we don't really need to include that. At least not in this case. So if I1 is bigger than I2, then we can say, because it is I0 is definitely not bigger than these two, because then it would already been Setosa. We can say if 1 is bigger than 2 and 0 is smaller than both of them, we can say it's versicolor. Print versicolor. And then else, we now know if it's not either of them, it's highly likely going to be Virginica. Print Virginica. Virginica, not call. Then we can see, get rid of these two, I'll get rid of this here. We got the order of Setosa, versicolor, and Virginica. Let's see if these orders are correct. From our original one here, Setosa, versicolor, Virginica. Setosa, versicolor, Virginica. We are correct. We are here. This is how you get from a word that shouldn't be in an equation, create them into their own columns, and then mark them with ones and zeros, or basically true and falses. And then eventually get them to return to their original values. This is how you do that. Pretty cool. One last thing before we go, I'll also tell you guys how to briefly do this as an input. So because this is a special list type, so remember there's double brackets here, no commas. You can actually take in your own inputs. So instead of independent, so let's do my input equals input. We're going to use the map command again. So we're going to do here. I might have not coded this for it. Guys, give me a second here. Just a second here. So we can use actually the map command to set our value to be something else. So value is going to be, we can use the map command to do, because these values are all decimals, they're floats. Input dot split. And if we actually give them the correct value, okay, this is also not going to work. Give me a second here. We never calculated anything. So we're going to do, okay, wrong statement. This is going to be my input again. And we're going to do value equals model.predict list value. I'll explain what this means very briefly. So we're taking the map, using map command. We turn the input.split, so that gives us back a list. Input.split, without any variables inside the sprint parentheses, divides it upon spaces, and then turns it back. And then the map command runs it over the float command. It becomes a float, and then if you do print my input, and then do print type my input, run this one here. I actually need to give it a value. Give me a second here. Okay, we'll ignore this for a while. I mistyped that. You can see this print my input give us 5.1, 3.5, 1.4, 0.2, or this is the input, and then this is map object at this. It actually still doesn't know what it exactly is. It's just a map object. It's a map object. And if we print it, it's a class map. Not a list yet, but a map. So what we do here is we turn it into a list. Maps can easily be turned into a list just by using list parentheses my input. So you can also just do list here. And then get rid of the list here. And then this will give you an actual list. Interesting. Model.predict. Oh, I mistyped it. So we got this, then list. So my input is now a list because we turned it into a list. Maps can be turned into a list pretty easily using this method. And then we do value equals model.predict my input. So remember, because this is a weird double, so list already has big brackets. It is double big bracket. It's double bracketing a list. What this does is make it into a 2D array. It says height and width. Remember, this thing has the height from columns and then width here. Vertically, it's height. So a column would be the height. A width would be a row. It has that. So we got to turn it into a 2D array for this to understand it as data. So we put another bracket on a list already, which already has brackets. And then we set that as value. And then this is just the identifier method, identifying method. So if we just print value here, we can actually see what it's doing in the background. See, this is the same as before because this input is what I copied from the first line here. If you do the second line here, remember this is variety versicolor 1, this is versicolor. If you run this again, do versicolor, get versicolor. This one is by far the biggest number because it's only -1, -4, -1. This is 0.8, this is 0.1. So this is the most likely, therefore it says versicolor. Simple enough. That is what it's doing. That is how you use map command to get a list of inputs, and then also how you turn just a bunch of numbers or a bunch of under one, and then find the biggest and then get them to what they originally were. And then also by using .pd.getDummies, you can get these ones to be just variety.versicolor, variety_versinica. So this was how you do iris flower. That would be it for me and for machine learning, I think, for your class today. I'll now hand it over to Aiden, who will lead us for the rest of the way. Thank you.